As mentioned, I'm Andrew. My main thing in Python is being a Django core developer. I'm known mostly for work on South and migrations, which followed it. And these days on Django channels and async Django, which is kind of part of what I'll be talking about here today. I used to live in London. I moved to the US 5 years ago. I now live in beautiful Denver, Colorado. And while I could go on about mountains for probably 3 hours, we don't have the time. And so we should probably get to the main talk. But the key thing here is asynchronous programming. Everyone talks about this as if it's a thing everyone knows, but like, what does it mean really? I've asked 5 different people and got 5 different answers about what this actually means. And I want to sort of take a few minutes to explain what I see it as and what it generally is perceived as, at least in Python. So to first talk about asynchronous programming, we talk about concurrent programming. Concurrent programming is the general term for doing things at once. As an example, a process that just runs in a single order like this, that's sequential, that's not concurrent. When we have things in parallel, that is concurrent. And there's more than one kind of concurrency. The key thing here is what we're talking about is the shared use of a single resource. Now, in a computer, that means usually the CPU. Most concurrency in the OS, with your programs, with threads, whatever, is just basically sharing CPU time. This actually dates all the way back to the 1800s and telegrams, when they literally had to time slice the time on the telegram wires. That concept still is used today to divide time on CPUs. And there's a lot of different ways of talking about concurrency. There's mathematical ways, like this proof language. This is one of my favorite proof languages, CSP. It is an amazing algebra for talking and reasoning about concurrent programs. You can write your program in it, you can prove it deadlocks, you can prove it doesn't deadlock at all, you can prove all sorts of things about it. Unfortunately, you can't actually write programs in it. There are other things inspired by CSP. Go, for example, is heavily inspired by CSP's design. Channels and Go routines and other things like that all draw directly from the way CSP is designed. But in general, we sort of want to move away from the abstract ideas and focus on what we actually use in the real world. So let's talk about the 3 main ways we do concurrency today. You've probably used all of these. The first and most obvious one is multiple processes. Your computer does this all the time. Like my laptop right here is running probably 20 or 30 different processes at once because it's just running an operating system. And in Python, this is the multiprocessing module. There are other options too. You can use os.fork if you want. You can use subprocess to spawn other processes. But in general, it's a very well understood kind of model. There's threads, which come in different varieties. Python threads are a little bit different to normal full OS threads. But in general, the difference is that multiple processes don't share memory. Threads do share memory. That's kind of the difference you see. And threads tend to just run whenever they want to. They schedule themselves whenever. And then finally, what is one of the oldest and also one of the newest, like they used it on Apollo, but they also use it now, event loops. And this is what, when we talk about async IO, what we're talking about in Python. It's also what things like Twisted were using beforehand. And there's a couple of trade-offs for these different kinds of concurrency. Multiple processes, by all accounts, scale best. Purely because if it's running in 2 processes, you can take the 2 processes and move one to a different machine, and you can keep doing that as long as your thing gets bigger. If you're designing a software for a huge site, like my work at Eventbrite previously, you have to do this because you have to be able to scale the site up beyond a single computer. The problem is the trade-off there, the cost, is that it does cost the most. You have to put a lot of work to make it scale like that, and it's also really difficult. Not having any shared memory means you're writing TCP, you're using service buses or microservices or HTTP. You have loads of different things you've got to handle, and it just gets a little bit annoying. Threads are easier in a sense because you've got shared memory, but they're also unpredictable. I'm sure many of you have run into threading in Python. When you run a thread in Python, at any point it can just go away and a new one can come in. Which means that if you're in the middle of doing something, oh, I'm sorry, it's gone now. You can't do that anymore. And We are saved from basic corruption, like the GILL saves us from having like our dictionaries corrupted, but you can still be midway through adding things to a dictionary and get pulled away. So they're kind of hard to work with. You don't know when things are going to happen. Event loops end up being a pretty good compromise. They are much more structured than threads. Like you decide when and where you're going to change and do things. You say, oh, I'm going to await here and have something happen. But they do still share memory. And so you get a lot of advantages of running on a single machine. Like it's much simpler. You can use much more of the machine's powerful CPU. But they're also much easier to program than multiple processes. And when we talk about asynchronous, in general, we mean event loops. That's kind of what we say, especially in Python, but in many other languages too, like Rust or JavaScript. We mean an event loop. We mean a thing that basically waits on events and runs them as they happen. What do I mean? Well, let's see. Here are 3 examples of asynchronous Python code. Each of them has an await clause. And what that means is when the code hits this line, it goes, OK, I have to wait for something to happen. And there are different kinds of events. The first line here waits for a timer to finish, in this case, a 1-second timer. The second event waits for a network request to return. The third event waits for a coroutine to exit. But crucially, all of these things have a point in time when they're done, and we can keep going. And so when you have code written like this, what Python and other languages do internally is they actually run a thing like this. They have the loop, hence the name event loop. And the event loop has multiple steps. First of all, it progresses all the networking and timers and like runs those things in the background. And then once that's done, it looks at all the tasks it has and says, OK, of all the things I've got awaited, which one of these is ready? And it picks one of the ready ones. It takes that, it runs it until it gets to an await, or it returns, and it finishes that task, puts any new ones it made onto the queue, and then just runs again. And it just does this really, really, really fast all over and over again. Now, one thing you'll notice here is that it only runs one task at a time. If your code in that green box does not await, if you write bad code that it sits there and like crunches for 3 or 4 seconds, the loop cannot run. It's not special Python. Like most of async.io is normal Python, written around normal Python features, so it can't grab control back from you. It's just waiting. In English, this is called cooperative multitasking. You must cooperate. And so one of the very common problems is you don't give back control. But if you do give back control, you end up with basically a process that looks a bit like this. All the different coroutines run in different slices as they finish or wait for stuff. If a thing is waiting to talk to Google or trying to wait for a timer, it just gets suspended and goes into the background. And that's kind of what we mean when we say asynchronous. But there's an interesting question here, which is, this seems like an interesting solution to the problem, and it is, but how exactly did we get here? Like, how do we get from Python's very early days, like Python is older than Java, to now? So I've made a small timeline, and by small I mean big, and this shows you some of the different things we've seen in Python over the years. So the very first thing we see, back in 1998, is the threading module. And threading is, if you read Guido's initial commit message, it says, making a Java-like threading module. So he's clearly inspired by Java at that point. And it gives you some very decent basic concurrency. It comes with a lot of problems, like I mentioned. You don't know when things are going to go wrong. It's kind of hard to write safe code between them. But it's really interesting, and it's a good start for Python as a big language. Back at this point, Python was still a very small language, and not many people used it. At the same time, stackless Python, which is most famous perhaps for EVE Online, was also invented. It's a very different way of doing concurrency. They basically allow a very, very large number of different things to run at once by removing the stack, which is one of the ways you track where things are happening. And that kind of continued. Stackless is still ongoing. They have a 3.6 release, but it kind of separated from Python's main line. It has always been its own thing. Then in 2002, Glyph releases Twisted. Twisted is the very first that I know of event loop implementation in Python that is like fully featured. All the concepts I showed you just then were there in 2002 in Twisted. It had all the things like waiting for network requests and waiting for timers. And at this point, the idea of event loops and coroutines, which we call things that run in event loops, kept going. So around when I joined Python in 2004, 2005, we see the first steps towards Python, the language, making it easier. Twisted very much had to invent its own subset of the language to make it work properly, whereas PEP 342 changes generators and says, okay, we're going to allow you to not only yield from a generator, but to also return values into it. And that's the start of allowing you to use generators to build a coroutine and an event loop framework. Later on, in 2006, we get greenlets, which are a different idea again. They're a bit more like threads, but they are also a bit like coroutines. And G-event and eventlet are the two things you will probably know, mostly G-event, I imagine, from that project. Greenlets are generally better than threading. The problem is, because they have to sort of hide the way they suspend deep in the code, it can still give you a little bit of that unexpected, like, will this function call suspend my code? I have no idea kind of problem. In 2008, we get the multiprocessing module. I remember multiprocessing being this big, exciting new feature. People going, oh, it's amazing, we can finally write efficient multiple processes in Python. Oh, there we go. And it was fantastic, and it really helps save a lot of the problems of like parsing things to and from. It does use pickle a bit too much, but we're not going to talk about that too much here. And then later on, we get further along, and we get to Tulip. Now, Tulip is Guido's attempt at writing his own sort of coroutine-based framework. There are other coroutine event loop frameworks in that gap, but essentially, Tulip is what becomes Async.io. And there's a PEP 3156, that sort of sets the stage for what becomes, in 2014, in the release of Python 3.4, I believe, the Async.io module. And that's kind of how we get to where we are today. I've been doing asynchronous code since Eventlet, back in about 2007, but I didn't really get involved until recently. And that's when I started looking at things for Django. So in 2017, I started looking at Django and went, okay, it probably makes sense that we have some kind of asynchronous code in Django. And so my first attempt, Django Channels 1, I made it, released it. It worked pretty well. There are many sites that still run on it, much to my terror sometimes, but they work fine. And then 2018, I sat down again, I changed things again, and made Django Channels 2. Both of those projects were affected by the fact that I had to support Python 2, which means I couldn't use Async.io, I couldn't use Python 3. Django dropped support for Python 2 later that year. And so that's when I started going, okay, Django has dropped Python 2 support, we can finally afford to go and do async properly. And so in 2019, we had a DEP, which is the Django version of a PEP, and we took that, and it's very long. I warn you, if you go read it, it's like 25 pages. I love writing. And that basically describes this future of how we can take Django and add asynchronous support into it while not losing normal synchronous support. And finally, it says 2020, like it hasn't landed yet, but the pull request is sitting in GitHub this week. So my hope is when the video goes up, this will be true. But this year, async views will land in Django. So Django 3.1 will almost certainly have those in it. And then the next step is having the ORM be async, probably in the next release after that. And then at that point, we have basically a full usable asynchronous Django, while leaving Django still, like, if you want to write synchronous code, and you should at first, you can still do that kind of stuff. And I want to talk a bit about what the problems I've run into and the Django community has run into along the way. I will preface this by saying no solution is perfect. I have some problems with Async.io. I'm going to go into them here in a second. But I can't give you a better answer, right? Like, I'm just calling out things here that are the things that happened, but there's not really a better answer. It's just showing you that, like, whatever you chose, something would be annoying. So the key thing to understand is I showed you that big timeline. What that means is that Async.io is based on that early work about generators. It's based on yield and yield from. That's kind of part of its history. Like Tulip was written very much with those features in mind before support for async.io landed in Python 3 and later. And so there are some weird side effects that come from that particular problem. The first one is you literally can't tell if a function returns a coroutine. Now, you think this would be obvious or doable, but here are two functions that both return coroutines. The first one is written in traditional, normal, asynchronous Python style. It is an async def. You can look at it and go, well, that's clearly an asynchronous function. The second one looks like a normal synchronous function. But the key thing is the way asynchronous functions work in Django is that, say in Python, is they are callables that return a coroutine. And that bottom one, while it is not a asynchronous function, it is still returning a coroutine, and so it counts as an asynchronous function. And so if, even as a developer, I can't tell the difference here, like there is no way to tell in Python these two things apart. There is a convention. There is a thing called asynchrony.isCoroutine function. It will tell you if you see one of the first ones. It cannot tell you if you see one of the second ones. And so a lot of Django, we have things like this. We have to decorate them to make Python believe that they are actually asynchronous functions. So that's one of the problems. And the other problem is kind of the opposite. Because of the way this calling works, which is that it calls you synchronously first, and then if you return a coroutine, then you're asynchronous, you can't have one function be both asynchronous and synchronous. It's just not possible as far as I can tell, and I've really tried for a long time. Take, for example, these two Django ORM calls. We would love to have this second bottom line work. I would like nothing more for that to work. The problem is that both of these particular calling styles first call _call. And then, if it returns a coroutine, the asynchronous stuff happens on the second one. But you can't tell when it calls you initially what it's trying to do. There's no asynchronous call. Like, if you think about it, the await keyword is very separate from the function call. You could write this as x equals objects.get await x. That would still work perfectly fine. And so because Python doesn't have asynchronous call, you can't have a function that changes based on how it's being called. You just don't know what's calling you. What this ends up meaning is you can't have those shared functions, so you've got to separate, you've got to namespace out your asynchronous and synchronous functions. Now, as it says here, I really wish we didn't have to do this. So you end up with things like this, where you can't have the same code work in both. You've got to stick an ugly .async or similar in there. Ironically, we can't even use .async now because that's a reserved keyword. So we have to work out a different thing. Like I have a prototype of this. Prototype does not work on Python 3.8. It's like, no, you can't do this, Andrew. What are you doing? So I don't know, .a or something. But this is kind of the solution we have to do for now. And these are both potentially solvable in some ways, but in other ways, they are core choices of the language. I probably wouldn't get rid of them because the ability to do this and have coroutines be objects is nice. Like in Python, everything is an object. That's kind of part of the language. And this just reflects that. It's just annoying that there's no separate asynchronous call for that reason. What this then leads to is having completely different libraries for everything you're doing. It's kind of a situation like you almost write in like a different version of Python. So as an example, sleep is different. You can't use normal sleep. It won't work properly. You can't use requests. You have to use an asynchronous replacement like HTTPX. You can't use like database drivers. Those all don't work anymore. You have to use an asynchronous database driver. Even when WSGI doesn't work, you have to use a replacement like ASGI, the one Django uses. And so I didn't want this to be true for Django, right? I don't want to be like, oh, a Django or something. Like, we don't have to maintain two whole separate projects. And so really, like, going into this project, I was like, okay, what can we do to not have that happen to us? How can we blend asynchronous and synchronous and let people write both? Because if nothing else, like having written a lot of asynchronous code, my first advice to you is don't do it unless you have to. Like, it's very complicated, and I'll show you some of how it's complicated. But I want to write 90% of my code in normal synchronous Python. And then when I get to the difficult part, the part that's really hard, that I want async for. But I don't want it before then. I don't want to have 2 different Django projects with 2 different Djangos. And the key thing here is async and async IO are not magic. They have a trade-off. Their trade-off is they do not benefit CPU-intensive code. They only work for IO-bound code, things that do a lot of like network calls especially. One of the nice things about this, of course, is that a lot of Django code is just talking to the database, it's talking to APIs, it's doing a lot of network calls. So in many ways, Django projects, more than, say, data science, are perfect cases for an async framework. Most of a Django process's life is sat waiting for something else to happen, which is the perfect case to have asynchronous code. And so we sort of sat down with Django and we went, okay, some parts of it still use the CPU a lot. They are CPU bound. Those bits do not need async. For example, Django has got a forms framework. Forms takes data, it validates it, it runs it and makes sure it's good, and it ranges it into a nice dictionary. That is all CPU bound. Like, unless you change it, nothing in there calls anything else. And so that's a perfect case of we don't really need to add async support to it. Like, maybe we do so that you can call a network request in one of the checking methods, but the actual code itself is perfectly fine synchronous. It doesn't, like, it will go slower if we make it async. But there are other cases, like the ORM, like I said, where it does make sense. And things like templates, where like template rendering is very CPU bound, but you do want to call things in your template, which means that even though the templates won't benefit, we want to still add async to templates so you can call async functions in them. So it's kind of a difficult choice there. The key problem we faced, though, was, as I showed you in the last 10, 20 slides, you just can't mix synchronous and asynchronous code. It's not a thing you can do. There is a little bit of extra work. So for a while, you couldn't call one from the other. I have developed, and Django ships with this, a good way of calling asynchronous code from synchronous code and vice versa. There's 2 functions in Django, or in one of its libraries, called sync to async and async to sync, that do what they say. They convert either way. And they're pretty good. They're kind of bulletproof. The problem is it takes about 1 millisecond to change modes. And if you're in the middle of Django, that can sometimes be too expensive, as I'll show you here. So this is the standard Django request flow as of Django 3. This has been the same for as long as I can remember. Like, I joined Django in 2008, 2009. It's been the same since. When I was editing this code, I found comments from like 10 years ago saying, oh, we should fix this. And then no one's touched it since. And it's pretty simple. A request comes in from the left here. It goes through some stuff, like looks at headers, works out uploaded files. It then like tries to resolve the URLs, runs middleware, then runs your code, which is the view, is what you write right at the end. This all seems well and good. And if you've watched one of my talks from last year, I was optimistic. I was like, great, well, what we can do is we can do this. And we can add in like an async head over here. And then once we've done like the async talking, because like this bit talks to the browser, has to be asynchronous, we can have both of those feed into a common single request path. And my goal was that was a purely asynchronous request path inside Django that both kinds of requests went through. The problem is, as I said, it takes about 1 millisecond to change from synchronous to asynchronous modes. And in that millisecond, you lose a lot of performance. Like, Django's overhead for performance is pretty much 3 or 4 milliseconds overall. So adding that much extra wait time is never great, especially when you've got to change backwards and forwards for all the different middleware. I think when I tested it, this added about 10 milliseconds to every request, which was long enough. I was like, no, Like, if we ship this, all existing Django sites get slower. That is not acceptable. No one will upgrade to a thing that makes their stuff slower. So instead of this, we have this. As you can see, we have pulled apart, and we have two totally separate and parallel request paths. And pretty much what that means is, like, there's a lot of duplicated code, right? Like, there's as much share between these two as we can. So basically, like, we have these two parallel request paths. I'm going to get back to it. Come on. The show must go on. And, like, again, I have tried to share as much code between them as possible, but you can see by this it's not great. Middleware in particular, we have two different versions of middleware now. I'm not going to go into details. Like, if you want more of this, then I'm sure at DjangoCon I'll go on for like 4 hours about this. But basically, the point here being that it annoys me slightly. And like, I would love to have this be better, but kind of part of being a programmer, of being an engineer, is you've got to work with what you have, right? Like, if I was like a theoretical scientist, I would live in the perfect world all day long, and I really appreciate them when they do that. But on the ground, like, I've got to ship Django. We've got to get this out there and get it used. And so while this is ugly, it hates this slide for some reason, it's still better than nothing. It's still a good solution, and it's only about 1,000 extra lines of code, which in the scale of Django is not too much. It's 1,000 nasty lines. Like, our Django fellows have taken a long time to review it because it's hard to review, but it's still important. And this is kind of part of what Django's job is. When I joined Django, I was kind of unsure what Django's job was. Like, what is a framework there to do? And in some ways, I think Django's main job is safety. Like, we're meant to be there for you to sort of understand these are the things that you can shoot yourself in the foot over. Things like insecure database access, SQL injection, like bad get parameters. Like, there's a whole list of like security attacks on websites I could list that Django prevents pretty much all of those. And that's kind of true for async as well. There's a lot of ways to shoot yourself in the foot over async code. These are just the 4 I could think of off the top of my head. There are many more than this. Deadlocks and race conditions are probably the most common ones that you may have run into as programmers. Live locks are my favorite because no one expects a live lock. And it's really annoying when it happens because, like, you write loads of deadlock prevention code, and what you're really writing is live lock enabling code instead. And it's nasty stuff. But, like, Django's job is kind of to prevent you from all of these. And one of the nice things about this, in a way, is that Python is made for this. I complained about async a lot earlier, but you'll never hear me say this again. The GILL is good, right? The GILL is an amazing feature of Python. For those who aren't aware, the GILL, GIL, stands for Global Interpreter Lock. There is a piece inside Python that basically stops 2 threads from accessing memory at the same time. What it prevents from happening is your code in a multi-thread situation both trying to read from a dictionary at the same time, write to a dictionary at the same time, and totally colliding. So there's it's not simple, but there's a sort of simply designed lock that prevents Python from doing that. What it kind of does, and what it does effectively, is it makes Python programs only run on a single CPU core. This was fine in the 90s, and all we had was single CPU cores. Like, these days, modern laptops have 4 or 8 cores, and Python is still stuck on one of them. If you do data science, I'm sure you've seen this particular problem. And the GILL is annoying, because the GILL is what keeps us on that single core. But in the case of concurrent programming, it saves us from all these different kinds of bugs, and many other ones too. And so I do want to call out the GILL here, and then the design of coroutines further helps. So if you remember, I said earlier that one of the problems with threads is that threads will randomly jump out of your code. You can't be sure that a block is atomic. Well, the wonderful thing with coroutines is it only ever releases control when you write the word await. So you haven't written the word await, you know it's not going to stop. Like, I know that no Python code in my process is going to run between these 2 awaits. You still shouldn't design a money system like this. I have many reasons why. But this is a good start. The idea of like the code that runs between those two blocks is in that process, as long as the power stays on, as long as the machine doesn't reboot, is atomic. And that's a really useful feature. And one of the things we can do in Django is like we can use these protections and add more of our own to help you not basically screw up, as it were. And trust me, I've been doing this for a lot of time, not as long as some, but quite a long time. You can screw up a lot. I've been writing async code for over a decade. I have never successfully written it the first time. I think pretty much every piece of code I write has some nasty deadlock or live lock or race condition in the first version. And the worst thing is, it's often not there when you run the tests, and then you ship it to production, it's like, aha, well now you've got more than one user at once, and we're going to completely blow up. So it's really, really hard to prevent against this kind of stuff, and in my opinion, it's Django's job to basically stop you doing this, right? Like, we can't stop you entirely. Like, people still write bad Django code. When I wrote migrations, one of my favorite things with migrations was people were like, oh, Andrew, well, these migrations are great. Does it mean that what I can do is I can change database tables at runtime? I was like, no, please don't do that. Like, oh, I can add a table per user. And I was like, oh. Like, so you can't stop everyone doing bad things, but you can help. You can try and guide them in the right direction. Here's a very common thing. I always want to call out for anyone who wants to start writing async code. Can anyone in the room tell what is wrong with this particular piece of code here? No? Yes. This is the correct code. You'll notice that there is a tiny piece of code difference in the two of these. The worst part is both of these will run without errors. If you run this code, Python will happily run the code, it will keep going, it won't raise an error, it will not run the log message code. And then right as the process exits in like a small font at the end of the thing, but like, oh, by the way, you didn't await this coroutine. Now, if you're running a server process, this can be like 4 hours later. So you're not going to see it. And so like this is the kind of debugging that like some people have problems with Python's design of awaits. Like this is kind of what I mean when I say like, what if we had like separate awaitable functions? Like if Python could tell that log message had to be a coroutine function, it could warn you at runtime or parse time about this. But of course, it can't do because of what I said earlier. So look out for this. At the same time, if you do this in Django in a few cases, we catch it. And we raise a warning to you that says, by the way, you returned as a thing without a coroutine awaited, you can't do that to us. And so like, these are the kind of small things that we can add to Django that we can kind of take and make it a bit safer. And in general, that's true of async as well. I think personally, async is the future of how we do programming. It is a great mixture of, you can just write normal synchronous code and ignore it and add a few pieces in. And to me, the best thing about Python is it's that kind of language. You don't have to start with a fully typed, perfectly written language like Haskell. But you can add in types. You can add in things over time. And I don't think many people will use async because most things don't need it. But when you do want concurrency, I think it's better to turn to than threading or multiprocessing. It's, you know, and this is maybe a contentious and unsure opinion by some people, but it is one I would personally say, having tried all three of those ways and more, that to me it makes the most sense. Because in many ways, Python is a language of, you know, in English we say pragmatism, right? It's sensible. We do things like a normal, achievable way. I feel like Python's whole goal in life is to be pragmatic. It's to like take problems and go, well, how do we solve this in a way that works for the normal programmer, right? It's not research. It's not doing it with infinite time, because I doubt any of us have had infinite time to write programs. If you have, please let me know, because it sounds amazing. Like, I have to sit down and write programs and ship them. And we get more time, we get tests, but at the end of the day, we've got to get things done. And I think that's kind of the point of Python, is that it's the language of getting things done. Django's tagline is the framework for perfectionists with deadlines. I've always liked that. It's like, well, we want to be perfectionists. We strive, we wish to be perfect, but we can't, right? We have deadlines, we've got to meet them. And so we get as close as we can. The question, of course, is what does the future hold? Like async in Python is still very young. You can tell that from these rough edges I've been showing you. My personal hope is that we can finally remove the GILL at some point, and then maybe that becomes Python 4, I don't know. Several Python core developers I've talked to are optimistic. They are not going to commit to it ever, but they believe it's possible. And if we can remove the GILL, the nice thing is you can take all that async event loop code, and you know the event loop I showed you with the big green section? You can just run 2 or 3 things at once. The event loop model scales to as many cores as you want, and you can just do whatever you like. It kind of all fits in the way you expect. And so if and when this happens, the GILL-ectomy, as it's sometimes called in a joking fashion, I really hope that that kind of is the power that takes async and drives it forward and makes it happen better. And more importantly, I think the thing for Python as a whole, and I mean both those of us who work on big Python projects and also you out there, like among this crowd are probably some future maintainers of open source projects. Let's make things understandable. Developer experience, the way you write software, is still incredibly important. You can think of a few small solutions, the things I've showed you in this keynote already, I'm sure. And there are way more of them where like, we can make async as well as things like multiprocessing and like many other concurrency methods safe, understandable, and still useful to use. And so like, I think that's the ultimate goal. Like, if you want to leave this talk with one idea, it's how do I take my complex problem and make it understandable for my users, be those normal end users or, in our case on Django, developers, right? We are end user developers, and it's important for us to make them useful. So please, I'd love you to try out some async stuff. And if you have any questions, I would also love to hear those. Thank you very much.